Yes. Welcome everyone to this week's ICTS String seminar. We have Shamik Banerjee from IOP Bhubaneswar. He's going to talk about MHV graviton scattering amplitudes from celestial current algebras. Over to you, Shamik.
Oh, hi. So thanks a lot for giving me this opportunity to talk here. So actually, maybe some of you have already heard this talk, but I decided to basically give this talk because this is kind of going on for the last 1 year or so. So, okay. Okay, so this is about the flat space holography or the spatial holography. So in flat space holography, the dual field theory has to compute the S matrix. Now the good thing is that in 4 dimensions, in 4-dimensional asymptotically flat space-time, the asymptotic symmetries are in infinite dimensional. So they act on the S matrix, and the word identities for these symmetries are the soft theorems. Now, since we have an infinite number of these symmetries for the S matrix, so it is natural to think that even in the absence of a Lagrangian description, we may be able to solve some simple examples. So this talk is essentially on that. So we'll just discuss a class of scattering amplitudes called, so they are known as the MHV or the maximal helicity scattering amplitudes, and they are simpler in a sense that we will explain as we go on. Okay. So this, so the basic thing is that, so we start with what, so this job is greatly facilitated by going from the Fock space to the celestial sphere by the Mechin transformation. So this equation 1, so that gives you the integral transformation, which takes you from the Fock space creation or an annihilation of operators, this A, epsilon, omega, z bar, sigma to these fields on the celestial sphere, which we write as phi h bar, z bar. And the thing is that here I will talk only about the massless particles. So I write the momentum of the massless particle in this form, and this h bar, so they have this form. So h is delta plus sigma by 2, and h bar is delta minus sigma by 2, and this sigma is the helicity of the massless particles. So now after this integral transformation, so these z bar, they are interpreted as the coordinates of the celestial sphere, which in the case of the 4-dimensional asymptotically flat space is an S2. Now the thing is that one can show just using the Lorentz transformation properties of these A's, that this phi h bar z bar, so that's a primary operator with scaling dimensions h and h bar. So this, of course, you can see that this has a standard form of the 2-dimensional conformal field theory, where h plus h bar is the delta, which is the scaling dimension, and h minus h bar is the spin. Now the thing is that this phi h bar z bar, so that's a primary operator with dimension HH bar under the Lorentz group SL2C, which acts on the celestial sphere as a global conformal group. Now, this delta is the scale. Yeah.
Hi, Shamik. Sorry, I have a question.
Yeah, yes.
So the question is, so I want to ask a question about general philosophy.
Yeah.
So this celestial sphere, I mean, is there any sense of where it is located? Because what you're doing here right now is you're taking something and you're just, you're kind of doing an integral over all of null infinity over all retarded time. This is
because it's an energy
holography, right? This is like just dimensional reduction in a sense.
Oh,
so,
right.
So, I mean, do you have any sense of where in retarded time this, in this work with Alok and so on, we argued that the celestial sphere should be near u equal to minus infinity.
Yeah, so, here, of course, we don't have a sense of u here because this directly comes from the momentum space where I have this energy and this ZZ bar. Now, the thing is that once you integrate, you are just left with ZZ bar. So that is a coordinate on the celestial sphere. So that can be reinterpreted as the coordinate on the celestial sphere. But yeah, so I don't think there is a particular notion. Actually, this is also related to the fact that, I mean, if I just look at the asymptotic free particle states, then there the particles are going outwards, and they just have this ZZ bar, and this omega is fixed. So once we integrate, so we are just left with that.
Right.
Well, the point is that this delta has something to do with that. I'll not go into that actually. So, but one can introduce a u here and do some things. In fact, that is what we do when we compute, because this integral transformation, this is not really, this is actually ill-defined if I work in GR. Okay, so for that, I have to introduce the time coordinate. I mean, that acts as the UV cutoff in some sense in this case. But the point is that, as far as one is concerned, there is no notion of where it is located in U. I mean,
but shouldn't this somehow be important? Because, in the bootstrap, I mean, even in the bootstrap in ADS-CFT, it was always important that there was locality. I mean, these operators in one, there is no good extrapolate dictionary for them, right? There's some very non-local operators. It's not like there's some bulk operator, you take it to the boundary and it becomes this phi. It's just a Mellin transform of something. So there's no sense in which, you expect a good OP or anything for these operators, right? Which is local.
So the OP actually I mean that I'll show. The OP is actually well defined. In fact, I mean that is whatever we do, the central role is played by the OP.
Okay, I can.
Yeah, so the point is that, but let me just briefly tell you that this delta is somehow, well, I mean, it has something to do with U, because the point is that if I make a translation in U, then this delta will shift. So that's how this space-time, the global space-time translations, the way it acts on these fields, this phi, is by shifting the dimension delta. So in that sense, this delta somehow knows about the space-time translation, but but it is not directly U actually. And so probably you can ask me there. The OP actually, I will just come to that in a few slides. The OPs are, well, I mean, the OPs are well defined. I mean, that we will see. In fact, that is the central thing. So can I just move ahead and then you can?
Yeah, thank you.
Yeah, so is it fine? I just. Hello?
Yes.
Yeah.
I think you can go on.
Yeah, okay, sure.
Right. Super.
So I can actually, so the point is that, so now the thing is that for whatever, what is happening? for whatever you do, this we treat this ZZ bar as independent complex numbers, or you can treat them as independent real numbers if you want to work in the split signature, which is plus plus minus minus. So that can also be done, but well, that is not very important. For as long as the Z and Z bar are independent, all these things go through. Okay. Okay, so now we can apply this transformation one, and then it gives us a, so we have this equation 3, and this S is essentially the S matrix of this massless particles, and I can do this Machine transformation of that, and that gives me the correlation functions of these fields, these phi's. Now, now to see that they are really, I mean, they can be thought of as correlation functions in a two-dimensional conformal field theory, is to just to look at that how the left-hand side transforms under the SL2C transformation, and we know that how the S matrix transforms under the Lorentz transformation, and that gives me this equation 4, which is essentially the way the correlation functions of a two-dimensional conformal field theory will transform under the SL2C. Now the thing is that, so these correlation functions, so they are the main object of interest in this talk, and now actually we have to see that what kind of word identities are satisfied by the spatial amplitudes. Okay. Okay, so now let's start with this subleading softgraviton theorem, which is this statement 5. So this has been written on the spatial sphere. So now you can see that we have these phi's, and we also have this S1 plus ZZ bar. So this is called the subleading conformally soft graviton, and this G plus delta ZZ bar. So that's a positive helicity graviton with weight delta, and this S1 plus ZZ bar. So that is defined in equation 6. Now the thing is that one can easily check that this S1, so this G plus delta ZZ bar is essentially one of these 5 fields actually, where this we have this sigma is equal to plus 2.
So sorry, Shamik, I got confused about something else.
Yeah.
Sorry, in this, where did you distinguish between the in states and the out states? I mean, which insertions are on scri plus and which are on scri minus?
Yeah. So these are these epsilons here. Okay.
I see.
So this epsilon is plus minus 1. Whether this A is an annihilation or creation of operator in the Fox.
I see. So all the OPs only have, I see, understand. Okay. So all the OPs only have to do with either epsilon equal to +1 or epsilon equal to -1, right? There are no mixed, mixed operators don't have any locality, right? Is that right?
No. That's not true actually. So you have also have the mixed ones. So
I see. Okay, fine. I'll wait and ask you.
So those are
okay, thank you.
Also there actually. Yeah. It is just...
Okay, thank you. Yeah.
Okay, so we start with equation 5. So this is essentially the rewriting of the subleading soft graviton theorem on the spatial sphere. So now what we do, so now the point is that, so this is of course in a form which, so this is already in a factorized form. But the thing is that in order to like know more about this, what one can do is that one can do this expansion. So what one can do is that one can expand this subleading conformally soft graviton, this S1 plus ZZ bar in this particular way. So we write S1 plus ZZ bar. So we expand in powers of Z bar. So the first term is J1Z, then the coefficient of Z bar, J0, and the Z bar square, which is J minus 1Z. And if I substitute this expansion in this equation 5, which is the subleading soft graviton theorem, then what I get is equation 8, 9, and 10. So J1Z, the correlation function of J1Z with a bunch of phi's, similarly for J0Z and J minus 1Z. And you can see that they have the standard form of the word identity of the SL2C bar or SL2R bar. I mean, depending on if you treat them as real or complex. But the thing is that these are the word identities of the SL2 bar. So for example, okay, so this can be seen more easily. So I have three currents, this JAZ, where A is 0 and plus minus, they generate the global SL2C bar transformations, and this delta plus 1. So this is the global transformation generated by J1Z acting on phi HH bar is essentially the action of L1 bar on phi. Similarly, delta naught is acting on phi is essentially L naught bar, and delta minus 1 is D bar acting on this phi. So that is essentially the action of L bar minus 1 on phi. So we can identify these with the word identities of the SL2 bar. And the thing is that, so in the standard way, so they become infinite dimensional. So we can define these local transformations, that is delta plus 1, n, delta 0, n is an integer acting on phi in this particular way, and then delta naught n and delta minus 1 n. So they are essentially the actions of this JAN, the modes of this current JA. Now one can also check that these modes, they satisfy this algebra, which we can call the SL2 bar algebra. So the main point is that, so we can see that this subleading soft graviton theorem is essentially the word identity for the SL2 bar algebra. So now, okay, now one of the thing is that, okay, so what is the OPE? So the OPE, so now actually what we want to do is that we want to compute the OPE between this S plus 1 ZZ bar, which is the subleading conformally soft graviton and a phi field, some phi HH bar ZZ bar, okay. And that, so what we have to do is essentially, that is the standard way that we can take this ZZ bar close to Z1 bar, and then we can expand the right-hand side of equation 5 in powers of Z minus Z1 and Z bar minus Z bar 1, and that gives me this, where I have these differential of operators, this JA minus P Z1 Z81 bar, which acts on these correlation functions, and they have this form. So this is like standard manipulations in the two-dimensional conformal field theory. Now, so we can see that this JA minus P for P greater than equal to 1. So JA minus P acting on this phi H1 bar. So so those are the SL2C bar, the descendants of the phi's. Okay. Now, so this equation 14, that as we take this z bar, say close to z1 bar, so this is also can be equivalently, so this can be written in the form of this OPE. So this is the OPE of the subleading soft graviton and the phi, and this has this form. So, or in other words, the S1 plus ZZ bar is essentially this object where this G plus delta ZZ bar. So that's a positive helicity graviton with a scaling dimension delta, and S1 plus ZZ bar is defined in this way. So this is actually the first example of an OP. So this S1 plus ZZ bar, so that's a soft operator, and this phi is a hard primary, and I can compute the OPE in this. So I can write down the OPE in this way. Okay, so that is the equation 18.
Sure. Sorry, Shamik, can I understand this OP as working on both scri plus and scri minus, because there's an antiportal identification of the BMS charges, and so this current that is labeled by value of Z actually acts both on scri plus and scri minus. And so, you know, if you try and take a certain value of Z, it can come close to both operator insertions on scri plus and on scri minus. So is this OP arising because is the antiportal identification somehow important to this OP?
Yeah, I think the conservation is this related to that actually. I mean, the fact that the charge at scri plus and the charge at scri minus, they are the same.
Yeah, but this is stronger probably, right? There's some antiportal identification of the current on the celestial sphere.
That actually, that is, you can see that if I just, so I have actually there is this implicit epsilon i's here, okay? So which are not there. So these epsilon i's are there. I mean, I've just not written them actually. But this epsilon I index is there, so which tells you whether it's an incoming or outgoing. Okay. So so they are represented on a single sphere, and the point is that if you do that, you get 5. Now, once you get 5, you can now proceed basically algebraically, and that actually so far, well, I mean, that does not really, the conservation of course is related to this, but once you write down the word identity, after that I think you can just proceed in a more standard
yeah, no, I agree with this. This I'm not surprised by. Would you ever see an OP if two phis came close to each other, not if the current came close to one of the phis?
But... So that's the main point. So I'll come to that actually.
You'll come to that. Okay.
Absolutely, yes. Yeah. So, but in order to do that, actually, I need this basically this OP between this S1 plus ZZ bar and the phi. So that is essentially the J phi OP that I need. I mean, in basically to know that. Okay, so now these are some standard things actually, which you can you can define a primary with respect to the SL2 bar, and that has this standard definition. So I'll just skip through this. Okay, and the second thing which we need are basically the Weinbergs soft graviton theorem. Now this S plus, so now I look at, so this is this equation 22, that is essentially the rewriting of the Weinbergs soft graviton theorem on the celestial sphere in terms of these fields phi, and this S plus this S plus not ZZ bar, so that is defined in equation 24. So this is defined in this particular way. So now delta is going to 1. On the contrary, in the subleading case, the delta was actually going to 0. Okay, so essentially the idea is that once you take delta to be 1, 0, -1, -2, and all the negative integers, so this J plus G plus delta, so that has simple poles there for delta equal to 1, 0, -1, -2, -3, and all this. And this S plus 1 or this S plus naught, they are essentially the residue at that pole. I mean, that is what it means. And the thing is that so now actually I know what is the correlation function of this S plus naught ZZ bar with phi, and this has this particular form. Okay, so now we play the same trick. Okay, so now one thing I did not really emphasize was that why this expansion. I mean, we expanded this S1 plus ZZ bar in power series in Z bar, but that expansion, that's a finite expansion because that stops at Z bar square. And the reason essentially, if you look at this subleading softgraviton theorem, you will see that essentially the power of Z bar, the highest power of Z bar is 2, and that's essentially the reason. So in this case, so now in the case of the Weinberg subgraviton theorem, you can see that the highest power of Z bar is 1. So now what we do is that we expand this S1 plus 0 ZZ bar in this power series, and once we expand this equation 25 in this leading softgraviton theorem, what we get at this equation 26 and 7, so which gives me the correlation function of this P0Z with a bunch of phi's, and this P minus 1Z with another with bunch of phi's, and they have the standard form of word identity in two-dimensional conformal field theory. Now we can look at the global space. So now we can look at the global symmetry transformations generated by this P0Z and P minus 1Z, and they have this form. So they are essentially the global space-time translations. Okay. So equation 29, you can see that under global time translation, your HH bar, they actually shift by half. So essentially the spin will not change, but the delta will shift by 1. So in that sense, I mean, the global time translation shifts the H and H bar. So in a sense, H and H bar know about the U in that sense, but not in a very direct way in this case. Okay. Okay, so now we can actually play the same game. So we have this word identity here. So that gives rise to an infinite dimensional algebra. And now we can define the modes of these currents P0Z and P minus 1Z, which you write as Pn naught and Pn minus 1. And they have this particular form. So you just multiply them. So they are the generators of the super translations. Okay. So delta n0 is this, and delta n minus 1 has this particular form. And as you know, this super translation, they form an abelian algebra. Okay, so now actually we also have to know what is the OP between this S plus naught ZZ bar, which is the positive helicity soft graviton, the leading positive helicity soft graviton, and a phi, and that one can easily check that it has this form where this P minus A naught phi HH bar and P minus A minus 1 phi HH bar, they are the super translation descendants. Okay. Okay, so now actually I think, well, I can just keep this part. It is the same thing actually. So basically, well, so I have these descendants, this P minus A naught phi HH bar and P minus A minus 1 phi HH bar, and I can compute the correlation function of them, and then they have this form. So we know them once we know what is the correlation function of these phi's without the insertion of this P minus A minus 1 or P minus A comma 0. Okay. Okay, so we can also define the super translation primary in this way, and so we can see that every this phi HH bar, so that has to be a primary of the algebra, the SL2 bar algebra, and
Can I ask a
the
question?
super translation. Yes, please. Yeah.
Hi. So if the global time translation shifts the delta by half, that's what you said, right? So does that,
delta by 1, h and h bar by half and half. Yes.
okay. So does that mean, like, when you think about this particular CFT, like the Celsius CFT, like it doesn't have a bounded delta, like?
Well, not so far actually. Yeah. I mean, it seems that, I mean, you have to deal with that actually. Yeah. Yeah.
And that doesn't create any particular issue, like?
No. It's actually
Some
it's
unitary constraint or something should give you delta.
well, that is of course not clear in this. So far, it is not clear. I mean, what is the, like, the 4-dimensional, that how the 4-dimensional unitarity is encoded here. I think that part is not clear. But the thing is that, well, it is of course there, and because the thing is that whatever we will get, I mean, those things they are true, and they are like hold for the standard things which we know. So they are there, but we do not yet understand. But the point, but let me emphasize one point, that the fact that this h bar, they shift, or this scaling dimension shifts by 1. So that is actually a good thing. So as we will see, actually, I mean, well, maybe we will not see, but if you work with these things, you will say that, I mean, that is kind of simplification. I mean, yeah.
Okay, thanks.
Sorry, Shamik, but your 2D CFT has complex conformal dimensions and negative conformal dimensions. So it's not unitary in the usual sense.
No. So one thing, yeah, so actually I did not go into that. So the point is that, to start with, so this delta, like in 4 dimension, so this if you take this scaling dimension delta to have the form, say 1 plus I lambda, where this lambda is real. So in that case, it's a unitary representation of the SL2C. So that is there. Okay, but the
S fields had negative conformal dimensions, right? Your
yeah,
S plus,
right. Yeah. So, but I am saying, to start with. So, I mean, if you just look at the hard operators, like
Right.
this size, I mean, not the S's actually. So those are like soft, yeah. And but the point is that if you take this scaling dimension to have this particular form, this 1 plus I lambda, where lambda is real, so then it's a unitary representation of
Yeah.
the SL2C. But the thing is that you can't really work, like you can't really confine yourself just to that part, because the space-time translation will shift that thing. So it
Yeah.
seems that you start with that, but then you have the space-time translation, which actually goes outside this, because delta equal to 1 plus I lambda. But then if you make a global space-time translation, delta becomes 2 plus I lambda. So that is not there in the SL2 unitary representation.
So
Now,
your 2D CFT is not considered to be unitary, right? Is that a fair statement to make, or is that wrong?
yeah, no, well, unitary. So there is some way in which the 4-dimensional unitary is here, but it is not clear that, like, not probably in the more standard way, I guess, like well, like these JANs. I mean, usually you will want this JN dagger to be JN minus, and I mean,
Right.
those are probably not the things that, yeah. I
think this delta shifting by half may not be the right way of thinking of it, right? Because if you make a global translation, you know how the how the local fields on Scri plus transform, which are not these phi's, but just taking the extrapolation.
So the point is that basically, well, I mean, if you can introduce this 3-dimensional picture instead of ZZ bar, you have fields on the Scri plus, like U ZZ bar. then you can actually, you don't need to go outside these delta, like delta equal to 1 plus I lambda. In fact,
No, I wanted to say something else.
Yeah.
This I agree, of course. Let's say we work within the framework in which you have. You see, even then, there's an inverse Mellin transform that will take you from this HH bar back to the UZZ bar, right?
Yeah.
And so this thing which looks like delta, actually a shift of delta, I think you can probably write as an infinite sum in terms of the same H's, the same principal series, 1 plus I.
Yeah,
At least
I
I
can,
think that should be possible.
So in fact, that has been done. I think Starsky and I think that has been done actually. So they have actually done this thing. So that can be done. But the thing is that it is just for the sake of algebra, it is just useful to just keep it there. I mean, but the thing is that I think these soft operators, soft operators, I don't know if they can all be written as some integral over the actually. Because these soft operators, I mean, they are not really obtained by global space-time translations. So they come in different ways, actually.
I see. Okay. Yeah, we can discuss more, but yeah.
Yeah. So that is, but I agree. So the point is that once you do that, you can write it as an integral over the principal series. So that is true. But but the thing is that, well, algebra, I mean, for the sake of algebra, you can just think of this field phi h1 plus half, h1 bar plus half as some symbol for that integral. Okay, I mean, suppose you just think in that way. But yeah, the thing is that you need to go outside this, I think, because of these essays. Actually, these soft operators, they are extremely useful, and they are not, I mean, they not necessarily lie on the principal series actually. Yeah. Okay, so let me just say, so the point is that, so now one has to see what is the algebra of this SL2 bar, contents and the super translations, and that has this form. So they actually form a closed L. This will form a closed L algebra, and the thing is that using this algebra, we can actually get the MHV amplitudes. Okay, so now actually, okay, so why these MHV amplitudes are special? So we know that. So let's just consider the tree-level scattering amplitudes in GR. So they have this property that the scattering amplitude with all plus, or just one minus and the rest plus, so they are not there. So the first non-vanishing scattering amplitudes, they have this form, this minus all plus, or you can take plus or all minus. So yeah, so those are the MHV bars. Okay. So we start with amplitudes of this form, where I have two negative helicity graviton and an n number of positive helicity gravitons. Now the thing is that the interesting thing about these amplitudes, which actually focus from the fact that the all plus and one minus and the rest plus, they are not there. So that is essentially the fact that there is no negative helicity soft graviton in the MHV sector. Now the reason is simple. So what we do is that if we make one negative helicity graviton soft, then the amplitude vanishes because of the soft factorization. So if I make this soft, then this just gives me the soft factor into this amplitude, and we know that this amplitude is not there, so we don't have. So that is the reason that the negative helicity soft graviton is not there in the MHV sector. Now, this actually greatly simplifies things in the sense that this MHV sector that should be governed by the symmetries generated by plus helicity soft gravitons on only, and we know that this is essentially the SL2 bar Cocorrelation algebra and the super translation Pn-1 and Pn0, which actually form a closed algebra. So now let's see that if this particular statement is true at the level of OP. Okay, so this is essentially, well, so these are actually the few terms in the OP between two hard gravitons, this G plus delta ZZ bar and G plus delta 1 Z1 bar. And this is true in the MHV sector. Now we can talk about this because MHV sector is closed in the sense that we don't have any negative helicity soft graviton, and also it is closed under OPE. Okay, and the OPE has this form. So the first term is, of course, so this term, this Z bar minus Z bar 1 by Z minus Z1. So this term, of course, is there in any amplitude. Now, the rest of the subleading terms are the ones which we are more interested in, and you can write down some of the terms. So the first term, the order 1 term, you can this is P minus 2 comma 0, and then I have a term which is like Z bar minus Z bar 1, and that has this form. Now you can see this P minus 2 comma 0 and P minus 2 minus 1, they're the super translation generators. And what we mean is that we just, so this OPE, they contain this descendant, this P minus 2 comma 0 acting on G plus delta prime, and this like P minus 2 minus 1 acting on G plus delta prime and things like that. Okay, so there are infinite number of terms, and all those things, they can be computed from the algebra in the standard way. And the thing is that you can also get them directly from the amplitude, just to make sure that what we are doing is right. I mean, you just have to make sure, because we still do not have a complete understanding of this. So just to make sure that we're doing the right thing, so we do it first algebraically, and then we compare this with what we obtain from the amplitude, and they exactly match. Okay, so this is one example of the OPE. So these are all outgoings, but the point is that so this corresponds to, say, epsilon equal to +1, but the point is that you can also have mixed OPs, and they can also be done in the same way, actually. Okay. Okay, so now actually what we can do is that, so from this OP, actually one can conclude that we have some not states in the game, and one way to see that is that, so I have this OP here, and now I can take, and now I can make this G plus delta soft. Now subleading soft, and that means I have to take this limit on G plus delta. So if I do this on the right hand side, I get this. So I have just used this one. But the point is that we know what this has to be. So this is a subleading. This is essentially this must reduce to this S plus 1 ZZ bar and phi H1 bar, where this phi is now this G plus delta 1 Z1 bar. And you can see, for example, we have this order Z, so we have this term Z bar minus Z bar 1. Okay, so this is essentially the S plus 1 ZZ bar, the OP between S plus 1 ZZ bar and G plus delta 1 Z1 bar, and I have this Z bar minus Z bar 1 term, the coefficient of that is this, but we know that this has to be this, right? That has to be J0 minus 1 G plus delta 1 Z1 bar. You can see in this OPE, the coefficient of Z bar minus Z bar 1 is essentially 2 times J0 minus 1 G plus delta 1 Z1 bar. Now the point is, so if this OPE is right, then we must have this form, which is written in this 44. And now we get, what we get is that, so comparing these two forms, we get these two relations between the descendants, one of which is this delta 1 minus 2 p minus 2 comma 0 G plus delta 1 minus 1 and J1 minus 1 G plus delta 1 Z1 bar. And we have this 46 here. This essentially comes from this order Z bar minus Z1 bar. And this first relation come from order 1 term, is p minus 2 comma 0. And you can see that these things have to hold. So these relations have to be true, okay? So now what we can do is that we can shift this delta 1 and write it in a more convenient form, which is this. So we get to, so this is, I mean, we can just recognize this easily. I mean, if we know, I mean, we know 2D CFT, and this should be treated as null states. That means if I insert this inside a scattering amplitude, then that insertion, I mean, that correlation function must be zero, and that gives us the differential equations. Okay, so now what we can do is that now actually we have just rewritten this OPE in this form, where I have just substituted using this null state relation, this L minus 1, P minus 1 minus 1, and things like that. Here, substituted it here, and we get finally, in terms of the linearly independent ones, this OP can be written in this form. So I have J0 minus 1, P minus 1 minus 1, and minus delta P minus 2 minus 1. Okay. So one can see that this OPE actually exists. I mean, so that is an important point actually, because without the OPE, we cannot do anything. I mean, nothing can be done actually. In fact, the point is that, well, so let me just go to the differential equations. So this is an MHV amplitude, okay? And we get these differential equations. Oh, sorry. So these are the equations that we get. So this is one equation, and this is the second one. So these equations are of this Nisnik-Zapochikov type. But the thing is that we have to be very careful, because we don't have any holomorphic factorization here. So you can see we have both L minus 1 and L bar minus 1 here. So that means both del Z and del Z bar are there. Okay. And the point is that for an endpoint amplitude, so we can see that an endpoint MHV amplitude that contains two negative velocity gravitons that satisfies n minus 2 coupled linear differential equations corresponding to n minus 2 positive helicity gravitons. Okay. Now these equations, so since, well, the thing is that, well, we have also checked that these equations are actually true. Now, what let me just show you. So this is a very standard actually, that these null states or these, so we don't really have a notion of null state here because we don't have a norm here. Okay, but what we can see is that strictly speaking, they are primary descendants, and we can set them to zero. But the thing is that they must be null actually. So that is what the S matrix will tell us. But we have not been able to show just purely algebraically that they are null, because we still don't have any notion of norm. But what we have shown is that they are primary descendants. So for example, let me take this primary descendant, is phi zz bar, which has this form. Now the thing is that so we know that this is a primary under the, so we know that in order to make sense, so this phi, this has to be a primary under the extended local symmetry algebra. That means the SL2 bar continental algebra and the super translations. In fact, the point is that we can get this phi just by depending that it's a primary under the extended local symmetrical algebra. Okay, and so this has a, so what we can do is that, so we can start with a phi which has this form, say J1 minus 1 P minus 1 minus 1 G plus delta plus some C. C is some undetermined constant times P minus 2 comma 0 and G plus delta. Okay, and this phi, so and then that can be written as phi 1 plus C phi 2. Phi 1 has this form, and these are the scaling dimensions of phi 1, and phi 2 is P minus 2 comma 0 G plus delta. Now the point is that one can easily check that this phi, so this in fact this phi 1 and phi 2, they are individually primaries under the Poincare group. That means this L1 phi I, L1 bar phi I, P naught minus 1 phi I, and P minus 1 naught phi I, they are all zero. So that means you can't get this C just by using the Poincare group. So, and so that means we need the local symmetries to get the C's, and that can be done easily. So first we impose this condition that this JAN phi is 0 for all n greater than or equal to 1. So what we get is now, using the fact that G plus delta is a primary under the extended symmetry and the computation relation, we get this. So what we do is that we have to, now we are left with only this J minus 1n with n greater than or equal to 1. And applying J minus 1n, what we get is that C is minus delta minus 1, which is essentially the right answer that we were looking for. Okay. So this C has to be this form, minus delta minus 1. So that actually comes from this by demanding this SL2 here.
Sorry, Shamik, could I just clarify something?
Yeah,
so
yeah, please.
These null vector states you found by demanding that the amplitude has the correct soft factorization. Is that
yes? Well, there are two ways of doing this thing. So that is one way. And now you can, now what I am showing is that you can completely do it in the standard sense, actually, like just by depending that, for example, this object that is phi. So one of the primaries was this, sorry, let me just, so this J1 minus 1 P minus 1 minus 1 and minus delta 1 minus 1 this. Suppose I want to get this one. Okay. So what we did was that we started with this state phi. Okay. So that is something plus some C. C is some undetermined constant. And then just by demanding that phi has to be a primary under the SL2 bar, then that just gives me this C.
Okay, but can you use these constraints alone to solve for the amplitude?
Yes, yes. So that you actually get n-2 such equations. So these are all the first order differential equations, and I think those can be solved. Like you don't get n, but you get n-2 actually.
Okay.
Yeah, but I think, for example, if I look at the 4-point function, because of the conformal invariance, it will depend just on z bar. I mean, I have just basically one undetermined dA, but I have two equations.
I have a sort of global question. So, I mean, the MHV amplitudes are known already, right? So what is going to understand from learning these extra constraints?
So basically the goal was not to get the MHV amplitude in this way, actually.
Right.
So what our goal was actually to see what are the symmetries of the, like, in a symmetrically flat space. And the thing is that of course these things, and the fact that these amplitude solves this differential equation, so those things of course are not known. So if you think in that way, then that's new. But the thing is that if I solve them, then what I get, so that thing was known. And the fact is that in this case, we have not, well, so this is essentially holographic way of computing the S matrix, because we have not used any kind of like bulk space-time methods to do these things.
No, but you started from the soft theorems, right? And the subleading.
No, but that is a word identity, right?
Yes. Well, okay.
So that is a word identity. So that is the SL2 bar. That is the SL2 bar word identity. So that's the thing, actually.
Okay.
Yeah. Yeah. So soft theorems, if you just look at this, for example 5, so they are, of course, the S matrices, they themselves, they have nothing to do with the bulk space-time as such, because they just talk about stripe plus stripe minus, right? So the soft theorems, they are statements about the S matrices. So as such, I mean, there is no bulk space-time techniques. I mean, the things moving through the bulk space-time or that, okay? But the thing is that the good thing about the soft theorem is that they can be reinterpreted as the word identities, and then the things completely change. So that is a good thing about it. Just like this is the SL2 bar word identity, or this was the word identity for the super translations. So these things are these symmetries are there, and they can be used to find out the S matrices. Well, at least this class, I mean, no, we don't expect that all S matrices will be obtained by solving these some differential equations, but at least this class you can actually. So that is the so yeah, so MHV amplitudes, but this is actually, honestly speaking, this is a new thing about the MHV amplitude. In fact, the point is that NMHV ones, they also solve more complicated equations, but we don't know like how to get them from in this way, actually. Okay, so this is the primary descendant. So all the things can be done purely algebraically. I mean, that is essentially the point. And then, okay, so you can do the same thing for the other state. For example, this psi ZZ bar. So that has this form. Okay, so you can, well, now the point is that if you don't like this, say, shell sphere or the Maclean transform, so let me just show that you can, so these differential equations, you can transform them back to the Fock space, and they have this particular form. Okay, so now I have, so this is now this in equation 67, this is a standard S matrix, and that solves these equations. Okay. Okay, so you can actually do the same thing for gluons. Okay, so for gluons, you get equations like this. You actually do the same thing, except that now the symmetry algebra is not the same. It is actually an SUN continental algebra, and you also have a subleading. Well, I mean, you also have one more algebra, which comes from the subleading softgraviton theorem. Okay, so the point is that, so let me just end by stating that what the things, what can be done, or like, well, what needs to be done probably. So the point is that what I have shown is that these asymptotic symmetries are powerful, and they can constrain S matrix to a large extent. Now, the point is that in some simple but not trivial cases, they can even determine them completely, at least in principle. Now, an important question is that what is space-time unitarity in this setting? So, and then of course, the other question, the more technical ones, are that from a more practical point of view, the existence of the OP means that the subleading terms in the collinear expansion have a universal structure determined by some symmetry. So in this case, it was the SL2 bar and the super translations. Now, the main point is that this universal structure, together with the soft theorems, that should be extremely constraining. And the thing is that it will be useful to know how to combine these with the more conventional ways of doing the S matrix bootstrap. And let me also explain you that this bootstrap point of view. First of all, you can see that this is basically, I think, the first example of an S matrix bootstrap where the amplitude can be computed and all the external states are massless. Because if my external states are massless, then the standard bootstrap is not very powerful. We don't have any interesting structure in the Mandelstam plane and all these things. But the thing is that, but still we can see that these, well, I mean, loops, there are infrared divergences and things like that. There are ultraviolet, infrared divergences. So those have to be taken care of. But even at the tree level, if you want to do the bootstrap with all external legs massless, then you don't have any interesting constraints if you do it in the standard way. But we can see that in this, from the holographic point of view, one can actually determine them, and that is more like the standard, like the bootstrap of the two-dimensional conformal field theories. Okay. So yeah, so just that this is the first example of that, where we have bootstrapped an S matrix where all external legs are massless, which can't be done in the standard way. Okay. Yeah, I think I'll stop here. So if there are any questions, then I'll be happy to answer.
Thank you, Shamik. Let's thank Shamik for a great talk. So we can take questions now. All right, if there are no questions, let's thank Shamik again, and let's meet next time.
Okay, thank
you, Shamik.
Okay, thanks.
Thank you for a great talk.
Okay, yeah.
See you.
See you.